morning, everyone.
Good morning.
How's everyone doing this morning?
Good.
Good. I'm Keith Brooks from the Education Department, but I'm here in reference to this context and program, which is put on by faculty development as well as the Friends of the Library. So we're very glad to have that partnership with the library between faculty development. And just also by way of announcement, next week, the Library Research Prize winner will be announced, so that's something to look out for. But then also in reference to what we are doing today in terms of a Faculty Excellence Award, every year faculty are nominated for service, for scholarship, or teaching. And today we are here because Dr. Rollin has been nominated for Faculty Excellence Award for scholarship. And Dr. King has achieved significant success in his research endeavors throughout his tenure here at Bethel, but his scholarship has led to numerous noteworthy publications and honors in the past year or two. Rollin epitomizes how to fuse chemistry, mathematics, computer programming, physics, and even philosophy and religion together to arrive at projects that are informative, collaborative, and applied. Rollin's collaborations have included both domestic, from the University of Georgia, Virginia Tech, Georgia Tech, and international. I believe that's Zurich. Or Zurich? Yep. He regularly publishes his research in peer-reviewed journals of the highest quality, for example, Journal of Physical Chemistry, Journal of Molecular Structure, and Journal of Chemical Physics. One of these, he has a proven track record of designing projects that are successful in a relatively short amount of time, and Rollin's research students have benefited from his success as well. So we are glad to hear from him this morning. Let us welcome him.
Thank you to all of you for being here. I know you're as busy as I am, and so without further ado, I'll tell you a little bit about what it is that I'm doing. My wife told me. I'm sure they wonder what it is that you're doing all the time. So I'll try to give you some idea of what it is that I'm doing. Most of my research has been clearly focused on this universe, I'll say first, but I have been involved in a couple of research projects recently which are applicable to discussions of other universes. So I will get there. I will be conscious of time and make sure that we stop by 11. So what is quantum chemistry? It really begins in 1925 when Schrodinger goes to Arosa. This is a picture from the cable car on the way down, taken by me. And you can see it's very beautiful. And he goes away for Christmas. He comes back, and he has the Schrodinger equation. And he publishes 4 papers very quickly after this point based on the Schrodinger equation. Dirac expands it a little bit in order to take account special relativity, which basically is the speed of light. And as a result, Dirac is able to say the following quotation here. In 1929, already, the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known. The difficulty is only that the exact application of these laws leads to equations much too complicated to be solved. Well, that looks a little hubristic, but he was basically right. He was basically right. There are many mysteries in physics, but a large part of physics and the whole of chemistry really have not changed since this equation was derived. What has changed? Well, to make a long story short, the most important thing that's happened since 1929 is the development of the modern computer. There have been many advances in theory. Many people have worked very hard on the problem, but the most important one from a practical standpoint is the development of the modern computer, which allows us simply to do calculations that were impossible by hand or on a UNIVAC or some other machine decades ago. So I put up here some characteristics of quantum chemistry today. First, high-performance computing. Some people use parallel machines. Lots of us use workstations. People are already making names for themselves running simulations on NVIDIA video cards. Any hardware that we can get, we will use. Quantum chemists use hardware. like nobody does. They don't believe us when we say that at first, but then when we tell them what we need, the people who work at the supercomputing centers, then they understand. Myriad methods of approximation. You can even sort of take the quantum out and do computational chemistry. You can make some really rough approximations. So you will hear different terms like computational chemistry, computational quantum chemistry, and so on. Generally, the more approximations that you make, the less reliable your answer will be. But the larger systems you'll be able to study. The research is very interdisciplinary, so as already mentioned, I've published in the Journal of Chemical Physics and the Journal of Physical Chemistry. And so that indicates that there's not really much of a line between these areas. You see computational biochemistry, molecular, similarly, molecular physics. There are many diverse objectives, the people who do computational chemistry. Modeling of active sites in drug design, that's one thing everybody can get, I think, can have some sort of appreciation for. I have good friends who work for pharmaceutical companies in the design of new drugs and drug development. Commonly, we're studying we're doing mechanistic studies of chemical reactions. We want to know how reactants become products. Spectroscopic signatures to support synthesis. So if we can calculate how a molecule absorbs a certain kind of light, then that can enable other experimentalists who are actually making the compounds to know if they made what they made or if they made what they thought they made. And that way, I avoid all exposure to carcinogens and don't have to wear goggles and everything. The experimentalists can do that. All right, so what does a computational chemist do? Ask chemical or theoretical questions, derive model equations, implement and refine algorithms, applications to chemical problems. Some computational chemists spend their whole careers on number 4. They don't develop theory, they just use other people's work to study chemical problems. And all of us are collaborating with other experimentalists and other theoretical chemists. All right, so April said I had to show you something like what I do. So the derivations can be tedious. We have a number of tricks that we use, which that's what those aren't doodles. We have a number of tricks that we use to draw diagrams to help make it a little bit easier to figure out how to write down and multiply all of these multiple index quantities together. But just to show you that there can be a lot of just sort of grit your teeth and work through it line by line. You would hope that a good physical theory would not require you to do this much. But unfortunately, we don't have that. That doesn't appear to be the case. So we write computer code. Now, most common, C, C++. There is still lots of old Fortran code around. You know, that generation is gradually retiring. But the code lives on, and so we have to be multilingual. But most of the development probably now is going on in C, C++. All right, so here's an example. I just want to show you a couple examples before I sort of focus on my one highlight topic. Here's an example of a project Ben Murren worked on. Last time I talked to him, he was working for a household chemical bio-feedstock startup company and was planning to go back to 3M. But he did some research. We got published in the Journal of Physical Chemistry in 2004. And this was a mechanistic study, so I didn't put the whole reaction up here. But the basic question was, when these two reactants combine, do the two nitrogens bond first, or does the carbon attach to the nitrogen? And after this, there are other steps to the reaction. That's not the final product. In an experiment in the lab, you can't bottle this product. This is a transient intermediate. It's gone in a flash. But on a computer, we can do anything we want. Right? On a computer, we can do anything we want. So we can combine the reactants any way we want to and calculate which one is lower energy. And we can ask other questions, too, about how a reaction happens. And if you understand how the reaction happens, you might decide to do different experiments down the road. We do a bunch of studies that we would call, or I've been involved in a bunch of studies I would call benchmarking studies. This was a paper that Taylor Mock did. He's the one on the left here. This is us in San Francisco at at a conference in Berkeley that was held in honor of my PhD advisor, Dr. Schaefer, last summer. It was a great time. Grant Lind, who's a current senior, is also in the picture. He didn't do this work, but it didn't seem right just to cut him off. So we left him there. And you can see there's a sea lion right there. So this was my first experience of observing the sea lions in San Francisco. But by benchmarking, what we do is, in layman's terms, we really try to kill it. That means that we use all possible computer power to get the best answer that we can. And these numbers can be used to test more approximate methods. So someone who can make more shortcuts and see if they can reproduce the result. And I've done a lot of work in collaboration with my friend Daniel Crawford at Virginia Tech. I have a picture of him up a little later. I've done a lot of work involving what happens to molecules when they get electronically excited. And Kerry Grove did, among other people, did a lot of this work. I didn't have a good picture, so she has her eyes closed up here. I didn't have a good picture, so I supplemented with this picture that's off the website of the Vanderbilt chemistry department. Kerry is now a third-year graduate student in analytical chemistry at Vanderbilt. But we got a paper published on how some substituted pyridinium ions will change their shape after they absorb ultraviolet light. And this was a case where some of the experiments had been done, some of the molecules that we looked at had actually been used in experiments before, but other ones had not. So we were kind of extending knowledge on what might work or not work in the future. All right, I'll get to my sort of highlight topic I want to tell you about here. The Kings go to Switzerland. So this is my sabbatical in 2008. And I don't pretend to be Schrodinger. For one thing, when I go to Arosa, I take my wife. And if you wonder what in the world I mean by that, then I'll let you go study the life of Schrodinger on your own. I was invited in 2007 to work with Dr. Wesley Allen, who's a professor at the University of Georgia, on some research that he had acquired money from the Templeton Foundation to perform. And this mugshot just doesn't do justice to the complexity of his character. So I included another picture down here. This is a farm, he calls it the family farm, on the border of Oconee National Forest that he cleared and grows by hand 30 miles away from his home. It has a phenomenal capacity to work, always doing new things. All right, so I need to give a little background here. What we were looking at in particular are some of the values, or the values of some of the fundamental physical constants. In the best theories of physics that we have, there's somewhere around 20 or 30 constants, which are dimensionless, that nobody can calculate. And this is somewhat disturbing to cosmologists and physicists, that there appear to be these numbers that we can't calculate, and besides that, their values matter. They need to have certain values. I'll come back to that in a minute. So the question is, what are the physical constants? Are they constant free parameters? Could our universe be similar in every other way but have a different value for some of these constants? Were the constants determined by some fundamental theory that gives only a probability distribution for them? So maybe the fundamental theory doesn't say what they are, but it says that they're likely to have certain values. We don't have such a theory, but these are possibilities. Or maybe they were produced just by luck. So there was some sort of random symmetry breaking event in the early universe, and these were the ones that we got, but it could have been different. Gabriel over here, my son, is just demonstrating that Arosa is also the home of the highest swing set in the world. Only the Swiss would do that, don't you think? I don't actually know that it's the highest swing set in the world, but I think it's 2,500 meters or something. Yeah. All right, so these numbers actually matter. So here's a couple quotes. We don't have a lot of time to get into details, but here's a quote from Stephen Hawking, probably the most popular book in this area that's been written. If one considers the possible constants and laws that could have emerged, the odds against a universe that has produced life like ours are immense. Here's one that's a little more specific about the constants. From Max Tegmark, who's a physicist at, now I want to say Harvard or MIT, I can't remember which. Virtually no physical parameters can be changed by large amounts without causing radical qualitative changes to the physical world. Now, science appears to be a little bit better at shifting what looks like design around than it does explaining it in some ways. So an example of this is the elements. So you can make a strong argument that the elemental abundances that we observe on Earth are consistent with their production in stars and then other astronomical events. However, stars are governed by what's called the nuclear strong force. And in the synthesis of the elements, you always have to pass through deuterium. And if the strong force is weaker, a little bit weaker, as in 5–10%, something like that. If the strong force were weaker than it is, then deuterium isn't bound at all, and you get no nucleosynthesis. So the stars don't make the elements. You can't go from a proton to neutron to helium, from helium to carbon, and so on. If the force is stronger, then helium-2 is bound. So it turns out two protons by themselves cannot fuse and make helium-2. Helium-2 is not stable. They have to have these deuteriums. So if the force is stronger, helium-2 is bound, and you can take your pick for what you want the consequence to be. If you started the universe this way, there'd be no hydrogen left in the universe, which means there's no star, there's no energy source or anything. If you did it right now, turn it on like a light switch, then the sun would explode instantly because all the protons would instantly combine. So we want to explain why or how all these different elements got produced in their abundances, and we can do that. But what we get, or what we have to pay, is some physical constants, like the constant that determines the strength of the strong force, as having a particular value. And the more research that is done, the more it's found that the values are quite precise. Some of them more precise than others. But some of the restrictions are quite tight. All right, so there's many responses to the anthropic principle. I just throw out a couple. Philosophers are making careers writing about this. You can read debates on this apparent fine-tuning in philosophy journals in addition to cosmology journals. Here's a couple. If there were an infinite number of universes, the appearance of one suitable to life should not surprise us. Many physicists are looking at this very carefully now. Again, we don't have a grand unified theory, but it seems to be growing in popularity that the theory will support the idea that there are many universes. That raises some other questions like, is that a satisfactory scientific explanation for everything, even if true? So what? Does it really explain why our universe is the way it is? Here's another response. This is a statement of what would be called the strong anthropic principle. The universe must have those properties which allow life to develop within it at some stage in its history. And you might wonder why. Why must it? Well, it's kind of a postulate, and you can believe this for various reasons. One of the more bizarre would be if you believed that we were evolving into God that would then create the universe. Which sounds very strange, right? Then it would be necessary that the universe allows life to develop, because otherwise we wouldn't evolve into God and we wouldn't be able to make the universe. But there's a lot of careful writing about this, and this is a little more complex, but I'll throw it out there. There may be other things that are also necessary for life. So one property that we take for granted that's very delicate is the floating of ice on water. Water is a very complex substance. If there are some other requirements, like the fact that ice floats, and there are many of these things, it may be that even 26 numbers doesn't really explain why you would get all the properties that produce life. So Tegmark has written about this. He's certainly not a theist. Actually, Tegmark's view in this paper that he takes is all logically consistent universes actually exist. So you can think about that. It's a 55-page paper, I think. Keep going. All right, so I've tried to give you some sort of pictures or windows into what people are thinking about and why there is now sort of a big project going on in science that I'm going to call the ultimate habitability quest. I'll read the second quote first. Barrow writes, "We need to know all those constants of nature whose values provide necessary conditions for the existence of observers." Why do we need to know that? Well, because this is a sort of data that you use to make your arguments. You're not going to prove that there's God or there's not a God, but you're going to use this kind of data when you're making your argument. Tegmark says there could be a large number of tiny islands of habitability containing life forms which would simply evolve by combining chemical elements in a manner different from ours. So what he's saying here is that, okay, you're right, we know now that if we take our universe and we take one of the physical constants and we change it a little bit, generally we just get chaos. In other words, a universe which is clearly uninhabitable. But even though we haven't figured it out yet, there may be other solutions to the problem. So you change this here, you change this here, maybe you bring up another force that's really weak or something, and you come up with other solutions. So this is what the people who are arguing about multiverses and anthropic principle and fine-tuning, this is what they want to know. What they want to know is what's necessary for life. It's a very, very difficult problem. Right? We don't even understand everything about life in this universe, much less understanding everything that might conceivably be possible. All right, biochemistry in our universe. So let's see what we can say about it. Interestingly, only one force really matters as far as the function of biochemistry itself, the electromagnetic force. We don't need to worry about nuclear processes. We don't need to worry about gravity. We really only need to worry about the interactions of negatively charged electrons and positively charged nuclei in order to describe the biochemistry that's going on in your body right now. So that's a good simplification for us. Secondly, and even better, the effects of relativity are mostly negligible. So most of our bodies are carbon, nitrogen, oxygen, hydrogen. These elements at the top of the periodic table really don't show many effects from relativity. Only when the speed of particles approaches the speed of light does relativity become important. So it is true that in those cases where we have heavier elements in our body, then that might matter. But often, we don't have to worry about it too much. I'm going to come back to alpha in a minute here, but the approximation stated in symbolic terms is that the non-relativistic approximation is that alpha is 0. Secondly, we often can get away with the assumption that the mass of the electron is very much smaller than the mass of the proton. We know the real ratio is about 1800 to 1, and we can take advantage of that when we're doing our calculations. And the non-relativistic Schrodinger equation is what we need to use. All right, let me tell you a little bit more about alpha and beta here. So alpha is one of these magic numbers. It's dimensionless. It has a value 1 over 137.0359997. Nobody knows why. Many people have come up with formulas. For a while, some people thought it was exactly 1 over 137, and they came up with complicated rules for why it was exactly 137, but it's not. 137.0359997. There's a story about Pauli, who worked at ETH Zurich. When he was taken to the hospital, he was taken to room 137. And he said, "I know I will die in this room." Because the room number was 137. And I think he did. I think that was it. Relativistic effects scale as alpha z. Z here is the atomic number. So that's just saying that the farther we go down the periodic table, the more important relativity is going to be. And there are some rough calculations you could do that will suggest if the value of alpha was as large as 0.2, you probably have no chemical bonding at all. It turns out that it kind of gets in the way. Now, I want to be clear that there are many proofs or arguments that the value of these constants, like the fine structure constant, have to hit narrow windows in order for life to be possible. And we can't touch the most strict ones of those, meaning the boundaries that we're able to put on the physical constants from chemistry, perhaps surprisingly, are much broader than the boundaries that the stability of stars and things like that have put on the physical constants. So other arguments for stable protons, the existence of a grand unified theory, and long-lived stars already require that alpha must have a value between 1 over 85 and 1 over 180. Very interesting. But that is not my research. All right, the other approximation that I mentioned that we can often make is the electron-proton mass ratio. So the mass of the electron in our universe is 1,836 times less than the mass of a proton. Nobody knows why. We haven't yet even a good argument for why they have equal charges. Most of us think that the electron and the proton have exactly opposite charges. And I don't think anybody can even give a real good argument. We know they're close, of course. We know they're close. But, this approximation we make, sometimes called a flies on an ox model. So you imagine an ox walking across a field. The flies move around the ox so fast that to the flies, the ox isn't even moving. The ox's movement doesn't affect the distribution of the flies around the ox. This is what we do in chemistry. When a molecule is changing, we assume that the electrons are always equilibrated around the nuclei. They can always keep up. They're not going to get left behind. And this idea is really the basis of all of our molecular structure. When we draw a molecule down, we're drawing a sketch of where the nuclei are, and assuming that the motions of the atoms are small vibrations around those equilibrium positions. All right, here's some of the details. This is the stuff that takes all the work that I'll spend the least amount of time on. But basically, when the fine structure constant is increased, that means the speed of light is going down. They are inversely related. Over here on the x-axis here, 0 is the non-relativistic limit, so there's no relativity. 1 is our universe. And you can see between no relativity and our universe, there's essentially no difference. This is on the left, this is the bond angle of a water molecule that we've calculated. Essentially no difference. So this is just showing what I said before, is if you want to know something about water, you don't really have to worry about relativity. But if the speed of light were lower, relativistic effects more important, the fine structure constant be larger, this would be what you get instead. So these calculations here, you can think of them as completely useless because they don't describe our universe. You can think about them as calculations on other universes, if you want, that actually exist, or other universes that might exist but don't. But many people are very interested in these kinds of results. So the different graphs are just different types of theory that we've used. But this is a sort of experiment you can't do in a lab, right? We're going to change the speed of light for our experiment here. But on a computer, if you're including relativity, we can do it. This is just a plot just to show you we can play with the mass of the electron too. It turns out the effect is opposite for the mass of the electron. If the mass of the electron is a little more massive, the bond angle of water gets larger, and the bond length maybe goes a similar direction. We'd like to be able to calculate the properties of water, as scientists generally are not yet very good at calculating the properties of water in this universe, unfortunately. So we'll start small and calculate the properties of the water dimer, which means only 2 water molecules. And here's the strength of the binding. This is the non-relativistic limit. You can see 2 times we cut the speed of light in half, or we go to alpha over alpha naught, so we scale it up by a factor of 2, the fine structure constant. You get essentially the same answer. And then if you push it beyond that, then this binding energy starts to get down. This is how tightly 2 water molecules are held in kilocalories per mole. Well, what matters? Does that matter if the binding energy is 4.3 or 4.6 or 3.9? Well, here's some back-of-the-envelope calculations. I didn't do these, Martin Chaplin did. But if the hydrogen bond strength that holds water together is 29% lower than it is. Water boils at 15 degrees Celsius. You can probably imagine as easy as I can what all the consequences might be of water boiling at 15 degrees Celsius. Quicker than that, proteins denature, although there's a lot of conjecture in there. We don't really know. Even 5%, the solubility of CO2 is drastically changed. And then this last one I want to highlight. If the hydrogen bond strength is reduced only 2%, there's no liquid density maximum at 4 degrees Celsius. This is a very delicate thing that water has, that is able to have a liquid phase that has a maximum density at 4 degrees Celsius. This is the liquid that sits at the bottom of our lakes, below the ice, and prevents lakes from freezing probably permanently, if not vaporized from the bottom up. So again, we can't calculate that number exactly, but if you look at the properties of other things, like isotopic versions of water and their hydrogen bond strength, you can make that argument. So we just went through and we calculated a bunch of different chemical properties. We'll skip those. We calculated a bunch of different chemical properties and tried to get some idea of what they would, what these chemical properties would be like if the mass of the electron were different, the speed of light were different. And our boundaries are definitely larger than some of the astronomical or cosmological derivations, but I still think they're very important because of this idea that there may be completely different combinations of the physical constants that will work for stars, but maybe they won't work for a molecule. So it's an important piece. We got this published last year, so I didn't have time to talk about it. We did have some students do some related research, but that results didn't get in this paper. We got this published in Physical Review. It was an exciting time. It took us a year. Just to give you an idea of how delicate this kind of research can be, one of the referee reports on this paper, which is published in a prestigious journal, Phys Rev A, it's a good journal. One of the referee reports said, this is the referee talking back to the journal editor, that the work was innocent. That the work was innocent. There were some other adjectives too, but think about what that word meant. That was code for, this isn't some kind of religious, intelligent design project that's going to get you fired from your job as head of the journal. It was some code for something like that. But to the editor's credit, we fixed up some things and did a bunch more calculations, so we were able to publish. So that was good. As far as we know, we are the first paper that's published in this particular area of ranges of possible physical constants for chemistry. All right, I just want to point out some of my collaborators here. These are guys I work with all the time. Here's David Sherrill, Georgia Tech, Daniel Crawford, I mentioned him before at Virginia Tech. This is Martin Kvok. He's the one who hosted me in 2008 when I went to the ETH in Zurich. Here's Fritz and Karin Schaefer. So this was Dr. Schaefer was my PhD advisor, and also there are some other people up there. And then these are my students, and I want to thank them all and thank you for coming. We have a couple minutes for questions. I'll try my best in a shorter time. If anybody has any questions. Okay, well, thank you. Have a good day.